organized, so I'm just skipping that. And if you have a topic that you'd like to present, we're always on the lookout, so please reach out to us. So with that, I'm going to hand it over to Mithun, who's going to talk about DistCp. Mithun's a software engineer in the Hadoop development group at Yahoo, and he works on many things, as catalog, Hive, DistCp, and some of the other things. So I'll let him introduce himself. Welcome, Mithun.
Hello? Okay. Okay, first off, I'm going to have to use my box for this. So, yeah. That's brilliant. No, that's not okay. That works. Hi. So right, I'm Mithun, and I'm going to be talking about DistCp. I might as well tell you right now, I have one gated slide that's going to come in the next slide, and one item of truthiness, which I will actually let you figure out for yourself. See if you can catch it. So my name is Mithun. I work at Yahoo on HCatalog, Hive, and a secret project called GDM, or I used to work on that. I used to be a firmware engineer at Hewlett Packard. I speak fluent Hindi, and I'm a national karate champion.
There you go.
So the last pretty evident is number 3, I don't speak Hindi. Let's move on. Prelude. Anyone who's used Hadoop for any extended amount of time, more than one cluster, would have found the need to copy data between clusters, and hence would probably have used DistCp. That's what DistCp is. If you use DistCp on Hadoop 20 or before, you use legacy DistCp. So, as for the command line, the slide is that visible. So, the command line is pretty evident what's going on. -m20 indicates the number of mappers to run. You have a bunch of source paths, and the last part is the target. So it does map reduce copies from sources to target. The algorithm is actually quite straightforward. It's exactly how you would write it. Step 1 would be to recurse through the input paths that we have. You make a list of all the files that you want to copy, along with the file size. You put that in the temp file. You split the temp file into 20 groups in this case, one for each map. Then you launch an MapReduce job, and each mapper does the copy of those files that are assigned to it. And that's pretty much the end. The key here is probably that when you split, when you calculate your input splits, you want to make sure that each mapper moves the same number of bytes. So that's sort of a uniform size input strategy. So that's I guess that's the SPN source part for legacy DistCp in Hadoop 1. Now, I think at some point I think DistCp used to lie somewhere in the swirling depths of the MapReduce source tree in an example directory next to another program called DistCh, which did distributed CH1. I have a feeling DistCp and DistC8 were written as examples of how you can use MapReduce to solve the non-MapReduce problem. The difference here is that DistCp actually does something that's useful in production, copying files. And so people began to add patch upon patch, hack upon hack, until finally you got this one file that's 1,500 lines long that combines the driver program, the input format, and the map definition all into one with no unit tests. This is legacy. Let's go to the beginning. So our story begins, as a few of these stories do, with a bright, exuberant, if excitable architect at Yahoo. His name is Venkatesh. I wonder if he's here. Okay, so Venkatesh is an accomplished technologist, and he worked on a fair few things at Yahoo. But his magnum opus was this project called GDM, or Grid Data Management. Now, this program was responsible for managing lifetimes of data on Hadoop clusters within Yahoo. It used to handle about a petabyte of data a day. This number is for last year. We'll probably do a lot more now. There are three things that GDM does very well. There are three things it does, and it does it very well. It copies data from warehouses to the cluster, and that's called acquisition. It replicates data between clusters, and that's called replication. And then there is the piece that erases data from the cluster when it gets stored. And that is inexplicably done retention. And apart from that, we have these gravy functions like user dashboards and workflow monitoring and so forth, but these were the three bits that mattered. And of those three, we cared about GDM replication, because at the core of it, it looks like GDM replication could have been written to use DistCp, because you don't have to write a MapReduce job to copy files, you could just have used DistCp. So it sounded like a good fit, except it didn't fit. There are the reasons why legacy DistCp could not be used in GDM. The first is programmatic interface was appalling. I mean, you had to call DistCp.name with string arguments, and then you would have to wait until main return. Main only return after all the files have been copied. So, and that can take hours. Worse yet, the equal size input format that we just discussed is hard-coded into DistCp. So there's no way for you to sort of override that, and GDM might have needed to do that. So this simply wouldn't fly. The second is, as part of an optimization in DistCp, legacy DistCp, one of the things we used to do was skip the copy of a file if that file already exists at the target and has the same contents. How do you know if they have the same contents? Simply by comparing file checks. And this is a good optimization. The only thing wrong with it is that you're doing it on the front end serially, which means you call main. In one of my experiments, a 200 gig data set took 14 minutes before the job even launched. And that's 14 minutes that GDM does not have. Let's take the example of a Uzi workflow. So assume you have a Uzi workflow that needs to launch when data is available in a directory. Now, assume now that that directory is being written to by DistCp. Now, when DistCp's map task commits the first file into the target directory would be created, and Uzi would launch the workflow. Never mind that you have 100 other files that need to be copied. So this would lead to premature consumption of data. You'd be lucky to get a failure in this case, because Uzi might not even know. So There are, classically, we've had workarounds for things like this. We would say, put in an underscore done underscore marker file, which is empty, but it sits in that directory, and then let Uzi code on that file. Now, I can't begin to tell you the number of things wrong with this whole run. If GDM produces, I don't know, 10,000 data sets a day, that's 10,000 done files that it is producing. And that's not something you want to do because of being under pressure. More importantly, what if that underscore done file actually exists at the source of DistCp? Now DistCp needs a way to be able to skip over that underscore done file. So the workarounds simply wouldn't fly. I mean, let's think about it. The only solution for this really is for DistCp to copy data to a temp directory and then provide an atomic commit into the final path. Now, there were other problems, but just to give you a flavor for why legacy DistCp simply couldn't be done. Now, needless to say, GDM went into production without DistCp. The first thing we did after GDM shipped and was hardened was to come back and to fix DistCp. We fixed all this stuff by doing a complete rewrite. The question you might have is, why rewrite when you might as well have just passed the pattern on top of legacy DistCp as generations before SQL? I'll explain that with an analogy. Are you familiar with Red's Streets Unknown Name on the Joshua Tree album? So legend has it that you could have spent more time on that one song than all the other songs in the Joshua Tree combined. And the reason for that was because the initial guitar riff was on a different time signature than the rest of the song. So they had a master tape on which they had both sides of the song. And they would come into the studio and try to create that transition from the first time signature to the second. And they worked on this for days, and then weeks, and then months after the rest of the album was done, and there was no end in sight. So that drove the music producer, the producer of the album, it drove him bonkers. His name is Brian Eno. So what Brian Eno did mitigate was he came into the studio one day before any of the band did, picked up that master tape and staged an accident whereby he wiped it clean by recording over it, and the band just had to record the whole thing over again. I think they got to the end eventually, but his reasoning is not unlike ours, which was the quickest way to the end was simply to start over and shed baggage. So that's sort of what we did. We rewrote from scratch. The new code is available in Hadoop 23 and Hadoop 2.0. There might be a patch available for Hadoop 20 on GitHub, so I will have to check. So what has changed? The command line is nearly identical. This is the only API that we were trying to be faithful to. I say almost identical because we did have to remove one ludicrous command line option, which we'll probably get to towards the end of the time. The setup time we reduced simply by postponing anything that could be done in the MapReduce job. We pushed to the MapReduce job. In this case, the checksum comparison between source and target. It made sense to do this in parallel and at the end. So we used to take 14 minutes to set up, not took 7 seconds before the job launch. The end-to-end copy time for a multi-terabyte data set, in one of my tests at least, was cut down from 17 hours down to 7. And I'll explain how we did that a little later. atomic commit. This is the using case. It means you can say minus atomic and specify a temp directory that's configurable. And then the data is copied to the temp directory and then pushed atomically to the temp. Programmatic use has improved. I'm not sure if that's visible to most of you, but we are no longer using string arguments. We're now, in this case, we're saying preserve the block size in the copy and set blocking to false, which means now it runs in asynchronous mode, which means if you call the DistCp execute, it launches a MapReduce job in 7 seconds and returns a Hadoop job object that you can now use to call for progress. There were other things that we added, like bandwidth throttling, etc. But these were the essential changes. And no discussion of changes would be complete without also discussing data quality. But before we do, I can take a couple of questions right now, if you have them.
So can you use the same thing within the cluster?
Yes, absolutely. In fact, you can also use it to copy data from your cluster. So the question was, can you use DistCp for the same cluster? As in source and target on the same cluster, the answer is yes. And that applies to old DistCp as well. In fact, you can use it to copy data from your local file system to EHDFS as well. And that should work.
Checking of the save files to the MapReduce port.
So we push the comparison between the send files in both hands, the MapReduce side, and what do you use to make sure you're not the same amount of data you use? One MapReduce side.
That's actually so easier. I'm not sure I completely understood your question, but I think your question is, because we are comparing checksums in the MapReduce phase, the distribution of the load is now not ready. That is actually a valid question. So I'll tell you how we mitigated some of that as we go on. So I'm going to use my second analogy now. This is a screenshot from one of my favorite films. It is The Prestige. You might have heard of it. The movie is about two magicians who duel one another in the turn of the century, and David Bowie plays Nikola Tesla, the master inventor. So in the film, a millionaire magician comes up to Nikola Tesla and asks him to build a teleportation device that is capable of transmitting a fully grown human over a distance of 100 feet in under a second. Tesla is able to foresee the repercussions of such a device, so he asks the magician, have you considered the cost of such a machine? The millionaire magician replies, money is no object. To which Tesla replies, that may be, but have you considered the cost? Now, in that case, he was referring to an orthogonal, unaccounted for cost, very specifically the cost of dying 1,000 deaths. We really should watch that. But I use this to sort of segue into a discussion of cost, orthogonal cost. So consider the following sentence. The time it takes to copy a file is directly proportional to its size, or else being equal. That's great for the textbook, but in reality, you're going to have long-tail jobs. By that I mean, in this example here, I have 20 files of 2 gigabytes each, all exactly the same size, and you're trying to do a copy, And it turns out that one of your map tasks completes way later than the rest. Now, if the files are of the same size, shouldn't they be equivalent? Why should you have a straggling map? There's another thing you might notice. Sometimes the file is slow for a very long time until it crosses a certain block boundary, at which point it speeds up again. So which might point towards perhaps the data node. So are data nodes equivalent? But eventually it's hardware. So you could have one of the data nodes with a slow hardware, for example, that's error prone, and it's not giving you the 100 Mbps you would expect on a SATA interface. You might have network-related retries, you might have NICs that are error prone. Bottom line is you're probably going to have errors for runtime situations that you have not accounted for. So your approach of balancing load based on file size while it is well-founded might not be eventually very effective. So I'm going to park that for the moment and examine the command line again. You see that the source paths in blue use HFTP, but the target cell is HDFS. Now, a lot of us here probably know what that means, but in case you don't, you use an HFTP path for a couple of reasons. For one, HFTP is an immutable path. So that's like using a read only. It's kind of like using a const reference in C++. You don't accidentally write it. The second and more important thing is probably that HFTP gives you immunity from RPC versions. So if you copy from HFTP, you can copy data between two clusters running disparate versions of Hadoop. For example, Hadoop 20 to 23, Hadoop 1 to Hadoop 2. So that's probably why you use HFTP. There is, however, a performance implication. As is evident from this drawing. Here we go. So, yeah. Let's say we have a user program that does the file system.get.open of a data file. And then you begin to stream the file. What happens in the back end is the data client library checks with the name node, figures out where the blocks are, and then opens a connection to the first data node. The data node that contains the first block and then you stream. And then once you cross the block boundary, the data client takes care of transparently closing that connection, opening on to the next data node, etc., until the file has been completely read. Now, it's evident here that if one of the data nodes, for example, the red one, has slowness for some reason, then all blocks served from there are going to be slow. Let's contrast with what happens with HTTP. Very similar, but completely different. You're going to have, so the client opens the connection to one data node. All blocks from all data nodes are then streamed through this data node. Which means you now have a persistent connection from a single data node, and everyone else is streaming through it. The problem with that, of course, is if you close the red one, the entire file is going to be copied slow. So again, this is not something you have too much control over, because you don't get to choose whom you connect to. Now, I would like to take a moment to look at what a long-tail job will look like. Let's assume that in a job, all the other mappers are completed except the map that's working on input split number 1. And this mapper is stuck on that one. That is the very first part. All the other mappers have completed their work and gone home. And this mapper, not only is it stuck on the very first file that's taking forever, it still has 9 files after that to complete. The unfortunate thing in MapReduce is that you cannot, for example, split an already allocated input split and then say hand it over to another map class. Now, and that's simply because the relationship between the map class and the input split is sort of scattered. There is no one else to hand it over to because the others are gone. So this actually opposes a clue to how you would get around the slowness problem. This is clearly a case of a map class that is written off more than it can shoot. Analogy number 3. At an all-you-can-eat buffet, the surest way to reduce the wastage of food is to reduce the size of your plate. Might explain something here. So yeah, how do you apply something like that to DistCp? Let's say you're copying n files, and you have 10 mappers. Ordinarily, you would create 10 input splits. What if you were to create 20 instead? And each input split is what? Roughly half the size. And then you have all the mappers, they consume one input split each, and that still leaves 10 input splits unaccounted for. Let's assume that we can store those on the DFS in a location that is sort of accessible by others, by all the mappers together. So when each map class completes the consumption of its input split, it can go back to the work pool and pick up another. It's kind of like going back to the buffet. The offshoot is that the mapper that is slow does not go back to pick up more. So his extra work, his second half is probably going to be picked up and done by somebody else. Now, the thinner you slice your input split, the better the performance is going to be. But that has to be within reason, because you really don't want one file being copied per input split, because you could have a million files and you would have too many small files in your workload. And eventually that will lead to input pressure. But you can find a sort of middle ground. The calculation for something like this, we have sort of formalized into an input format called the dynamic input format. This is written in a manner that's independent of file copy, so you can technically use this as a separate MapReduce library and not use it necessarily in the DistCp context. But it is checked in along with DistCp at this time. The performance in the worst case, the performance is not very much worse than the uniform size input format that was used in the past. But in the best case, this is how we reduce things from 17 hours down to 7. So the white space was sort of the work that we have in the future, to summarize, we now have DistCp, which works with the uniform input size, format. That is the default strategy. The dynamic strategy is something that you could request for, depending on how your cluster is behaving or what your data looks like. In the future, we would like to add a way in DistCp to copy files on a per block level. Currently, the unit of transport right now is per file. We'd like to parallelize this so that we copy every block individually and then stitch it up at the end. We already have a path for it, it just needs to be formalized. Apart from this, we would also like to formalize the dynamic input format as a first-class application master in Yarn. because eventually we would like to code this as a master worker paradigm. In the master worker paradigm, instead of sort of shoehorning it into work with mappings. With that, I am done. So if you would like further questions, I know. Great. Well, thank you very much.